Welcome everyone to the first class on variational methods. Today I will start with an introduction and more of an overview. So today will not be very technical, it will be rather general. And the aim of today's lecture is to firstly give you an overview of variational methods and what they're about, what kinds of problems you can solve in the context of computer vision with these techniques. And the second aspect of today's lecture, at the same time, essentially, I will bring in some of the things that we do ourselves. This may be of interest for those of you who do not know me, who have not heard any of classes with us. This will, today's class will also give you a little glimpse of the kind of research that we do in computer vision. This is our research team, as it is right now. I think this is a more or less up-to-date picture of our group, the computer vision group. We are located right there in this corridor. So there's a number of postdocs in our lab and PhD students working on a range of topics in computer vision. Not all of the people in the lab are doing variational methods, but a substantial part of them are working on this line of research. What kind of research is that? Well, computer vision has many fascinating challenges, and one of them, maybe the most classical problem in computer vision, is a problem called multiple view reconstruction. The challenge is a challenge that you're all familiar with from your own lives. You walk around in the world, you see images of a 3D object, and you want to infer the 3D geometry of that object. You want to have a three-dimensional model of what you see in these images. Why you would want such a model is an important question. Often in research, actually, people tackle a problem. They don't ever ask themselves, why would I want to solve that problem? I find this is useful to think about for yourselves. What might be potential applications? What might 3D models of the world be good for? But you can imagine once you have a 3D model, there's a lot of things you can do. For example, you can do recognition of faces. It's much more informative to have a 3D model of a face than just a picture. And for example, face recognition algorithms that just are picture-based can be easily fooled. If you hold a photograph of a person up to the camera, then the face will be recognized, although the person isn't actually there. With 3D techniques, this is much more difficult. You would have to have a full 3D model to hold up to the camera in order to fool the recognition
or video.
Or video. So there's quite some challenges that you can tackle with 3D models. 3D models of the world are used frequently, more and more so in computer graphics and in Hollywood movie productions. If you want to do special effects, often it helps to have a 3D model. One of the things you can do once you have a 3D model of a scene, you can relight the scene later on. So once you film the scene, and then the movie production crew says somehow, the illumination isn't catchy enough. We want to change the illumination. If you have a 3D model, you don't have to record the scene again. You can just relight the scene after, because you have the surfaces, you know how light interacts with surfaces, how it gets reflected. And so with that geometry, you can actually do lots of things. You can retexture the objects, add a different texture, and create all sorts of cool effects. I mean, if you go to Hollywood, watch Hollywood movies these days, you will see tons of effects. And many times you're not even aware that there are special effects involved, because often they enter on a level that is so subtle that you don't realize that there was a retouching. It's okay. But there are other applications, of course. For example, one application of 3D modeling would be in plastic surgery. It's a huge market in the medical domain. You will want to know, well, can you fix my nose if it's a little bit weird? What would it look like if I fixed it? And what you need is some kind of 3D model and some way to acquire it. These problems, in particular, this geometric reconstruction problem, from a mathematical point of view, is a problem of infinite dimensional optimization. And this is very important to understand. Why is 3D reconstruction a problem of infinite dimensions? The way you can see that is, let's say I take a wild guess at what the 3D model is. Maybe the simplest guess will be it's a sphere. So I start with the model of a sphere, saying, is that a good guess for what I see in the images? Of course it's not, but let's start with some random guess. Once you have a sphere, you can basically go through the space of all possible surfaces by deforming that sphere. And how can you deform a sphere? You can deform it in infinitely many points. So let's say we start with a sphere, and then we can create protrusions of the sphere or indentations of the sphere and create lots of new surfaces. And how many protrusions and indentations we can create? Well, we have dimensions to the problem as many as we have points on the surface. And since there are infinitely many points, I can perturb that initial surface in infinitely many directions or dimensions. And these are all independent dimensions to the problem, and so that gives you an intuitive understanding why geometric optimization is a problem of infinite dimensions. And in infinite dimensions, the variational methods come into play. So variational methods are a form of optimization techniques, often particularly suited if you have very high or infinite dimensions. Let's go back in history to see where did that all start? Where did the variational techniques begin? And it turns out this is actually a very long history. Many of you may have seen such a construct in technical museums. Who has not seen this kind of thing? Okay. So what it is, you see it here, is there are 4 possible paths, and the idea is that you place 2 balls, or multiple balls, up here, and let them roll down these paths, and the question is, what is the fastest path to reach that goal? Mind you, it's not a question of what the shortest path is. You all know that the shortest path is the straight line. How many believe that the straight line will also get you to the goal fastest? Nobody. Very good. What do you think? How many believe that this path up here will get you there faster? How many believe that one of these paths will get you there faster? Most of you. Very good. So you have a good intuition. Indeed, one of these paths, I must admit, I don't know off the top of my head which one. I suspect this one here, but I don't know. One of these lower paths will get you there faster. And so the question that was asked very early on in history is, which of the 2 balls, this one or that one, for example, reaches its goal fastest? This problem is a somewhat simple problem. You can solve it as a multiple choice problem. There is 4 possible choices. One of them is the fastest. The true question and the interesting one is not so much which of these 4 passes is the fastest, but if you could randomly create your favorite path, which one would it be? Which path would lead you to that goal the fastest? And that is a problem, again, of not 4 possible choices, but of infinite dimensions. Why? Because if you look at this x-axis, let's say down here, this path is a function, the height at any point x is your function, and you're optimizing over the space of all functions, basically all height maps from this x-axis. And so there are infinitely many points where I can perturb a given path and create a new path. And I'm asking the question then would be, what is the perturbation? What is the optimal path that leads you to this goal fastest? This problem has been studied extensively in history. It's called the brachistochrone problem. So it's a very old problem, and it was solved by Bernoulli. Many of you know Bernoulli, a well-known mathematician who did a lot of work in statistics as well, but this is a work on this variational problem of finding the path that leads you, again, from this point to that point in the fastest possible way. And this is in fact his solution. This is his original writing. I must admit I didn't go through it in great detail. It looks a little complicated at first glance. What I find most interesting is, first of all, it seems to be a constructive proof. He tried various paths, as you can see here, and tried to figure out some criterion that told him which was the best. What is most interesting is actually the date. This was done in 1697, and so you could safely say that 1697 is possibly the birth of the variational method, because this is often considered the first variational method. Since then, a lot of time has passed, since the 17th century when it all started, and today variational methods are used very frequently in many fields of sciences, in particular in the field of computer vision and image analysis. There are many examples of variational methods and optimization methods in computer vision. This is image segmentation. These are just about 10 or 15 papers in this line, but there's really thousands of papers in all of these techniques. Multiple view reconstruction, the problem I just mentioned, is also a classical problem, and there's again many papers. This is maybe one of the pioneering ones for Jurassic Kiriven in '98. Both of these researchers are still active in Paris and in Nice or Sofia Antipolis. And optical flow estimation, another classical image analysis problem, where actually this is often, this work of Horn and Chunk in 1981 is often considered the first variational method in computer vision. Computer vision as a field itself is almost as old as computers. In fact, there's even older works that try to resolve computer vision problems before computers ever appeared. So early 20th century, but it took a long time, mainly until '81, that variational methods were introduced in computer vision. The reason is that variational methods, in order to solve infinite dimensional problems, typically you need a certain computation power. And it wasn't until the 80s that you actually had it. And it isn't until the 90s and in fact 2000s that now the variational techniques are becoming increasingly popular. Because today we can solve variational problems very fast using graphics hardware to accelerate large-scale optimization. And so as a consequence, the variational techniques are becoming very popular these recent years. One of the issues with all of these classical approaches, and these are in fact some of the most famous papers in image analysis, one of the issues with them is that the cost functions they propose to minimize are not convex. And so one of the things we will also learn in this class on variational methods is a little bit about convexity. What convexity means, what advantages it has, and to some extent how you can reformulate problems with convex images. Why would you want to do that? Let's look at the schematic plot. So the idea of variational and in general optimization methods is that you try to solve whatever problem you have as an optimization problem. It means that, let's say, your space of conceivable solutions is a two-dimensional space in this schematic drawing. So you have that dimension and that dimension. In other words, you have two parameters to optimize. then the idea is that you set up a cost function on this two-dimensional space, which assigns to each configuration of possible parameter values, it assigns some cost or quality criteria. And that cost encodes somehow how well does that configuration solve your problem. What do I mean by that, solve your problem? Let's look at the multiple view reconstruction problem I showed you in the beginning. What I mean is you can take an arbitrary surface with some color on it and project that surface into the various images you have observed. And then for each image you can check how well does the given surface match, the projection of that surface match my observation. And that matching score is your cost. Meaning, and in practice the convention is that a low score means a good match and a high score means a bad match. And so in the end you can say, now find the configuration that gives me the lowest, that is the lowest cost, that has the lowest score. This is a pure convention, I should say. Sometimes you find cases where people say they want to maximize something. So optimization is a very general principle. In practice, of course, it really doesn't matter if you minimize a quantity or maximize a quantity. It's just a convention that in this domain, often people minimize expressions. For example, if you work in different domains, economics, for example, and you want to devise a strategy for your company, then you want to maximize the gains, for example. But you may also want to minimize the costs, so there's some, the key essence is there's some kind of externality principle. And whether it's minimization or maximization really doesn't matter. You can actually convert a maximization problem into a minimization problem just by putting a minus sign in front of the cost. That inverts the whole thing, and then whatever was the maximum before is the minimum. But the question then boils down to, once you have a cost function, finding the configuration of lowest cost. And as you can see in this example, the difficulty is if your cost function is not convex but has multiple minima, then it's not easy to find that configuration here somewhere of lowest cost. How would you do it? Well, in a two-dimensional problem, the life is easy. What you would do in a two-dimensional problem is you would discretize your space on a regular grid as shown here, and then just try every configuration on that discrete grid. At least up to the grid resolution, you will find the optimal in this way. You try all solutions and you take the best one. That strategy is very naive, of course, but it works surprisingly well. And actually, if you don't know anything about your cost function, it's not even the worst strategy. It's actually, for general cost functions, very hard to devise algorithms that are really better than a complete search. And in fact, there's been lots of algorithms in the literature which, in the worst case, are no better than a complete search. And you can imagine the complete search is very easy to implement. It's just for loops, right? You have a for loop over this discretization, a for loop over that, nested two for loops, and then you try every configuration and always retain the lowest cost, and if it's not the lowest cost, you just keep iterating. So this is simple to implement and actually works quite well in 2 dimensions. Maybe also in 3 dimensions. And potentially you will get complete search working in 5 or 6 dimensions. But beyond that, it will become very intense. Why? Because if you have n discretization steps for every parameter that you need to optimize for, then the complexity of that algorithm grows exponentially with the number of dimensions. And that's very bad if you have high dimensions. And as I was arguing, surface reconstruction is a problem of infinite dimensions. In practice, of course, you tend to discretize things, and then dimensions are finite again. But still, the dimension will be very high in problems. And if you have thousands of dimensions, you don't want to do a complete solution, because the algorithm will not terminate in your lifetime. So somehow we are stuck, once we don't have convexity, to actually find the global optimum. In practice, what people often do, if they don't have convexity, is they initialize somewhere and find a locally optimal solution. And we'll learn a little bit in class how that is done. The other thing, as I said, we will learn is how you can go from a non-convex energy to a convex one. Why would that be good? Well, with a convex energy, you can actually efficiently find the globally optimal configuration. That's a little bit, I should admit, simplified. If you have an arbitrary convex energy, it's not always clear how you get to the minimizer in the fastest way. But in principle, for very large classes of convex energies, there are today algorithms that can do it. And so convexity is an advantage, not just in 2 dimensions, but even more so in higher dimensions. And if you have very high or even infinite dimensional problems, convexity is a very crucial thing. To give you an idea of an algorithm, we'll see it later on, that leads to the global minimum. It's an algorithm that, again, you're familiar with from your own lives. It's called gradient descent or steepest descent. Who has not heard of that term before? Okay, very good. So then I don't need to explain the steepest descent. All it does is you initialize somewhere and you go downhill. And in fact, at any given instance, you check what is the most downhill direction, what is the direction of steepest descent. And you can do that just by computing the local derivative. It tells you the slope and it tells you which direction is the way down. And so the steepest descent is exactly the strategy you would pursue if you were hiking and someone was asking you to go down to the lowest, to the valley in the fastest possible way. You would take the way of steepest descent. That would get you there fastest. If you survive it is a different question. If you're in mountainous terrain, it may not be a good idea, as you know, to take the steepest way down, but it's definitely the fastest. Here's some examples. So today I will mostly talk about examples of variational methods and the technical details behind it, the mathematics behind it, we'll learn in the course of the class. So let's take an image like this one, and as you can possibly see from where you are, it's a little bit noisy. There is a certain amount of noise in the image, and denoising of images is probably one of the most classical problems in image analysis. This becomes important, for example, if you have aerial images, you have a lot of noise with the atmosphere, atmospheric noise, so there's very different kinds of noise. Or if you have images, if you have digital cameras, often today you can take images in very low light conditions. But what you tend to see if you take images in low light conditions are these kinds of noise problems. Because there's not enough data, there's a lot of noise, and so these images will be noisy. And one of the challenges would be, so when I talk about images, by the way, in this class, images are mappings from a domain I call omega to either R for gray value images or R3 for color images. That means a function f that assigns to each pixel some color value, RGB value. And omega is a subset of R2, so this is often called the image plane. So that is the image plane, some subset of R2, this is omega, and at any point you have a color. Of course, the truth, as you know, is this is a digital image. So you only have a finite number of pixels. It's almost infinite, I should say, with modern cameras. You have megapixels, and so the approximation that your space is continuous is actually becoming better and better with higher resolution cameras. And we will learn in the class, this is one key aspect of variational techniques, is that they consider space as a continuum. And there are advantages in doing so. One key advantage, to name it right beforehand, is if you discretize your image as it is actually stored in the computer as some grid, then somehow your algorithms often depend on the choice of the grid. If I take this grid, I get some solution. If I take a different grid, I get a different solution. There are algorithms that are designed on the grid level. And so in practice, however, we want to devise algorithms that are independent of the choice of grid. Meaning whatever image processing I do should not depend on how I hold my digital camera when taking the image. Because that imposes a certain grid, but the solution to the algorithm should be independent of the discretization and of the choice of grid. And if you work in a continuous setting, there is no notion of a grid. There is no grid, so whatever I say actually applies to a continuous world. Here is a very classical variational approach to image denoising, and we will learn a little more about this. It's an approach that, due to the three authors, is today called the ROF model. It's called ROF model, and that stands for Ruder, Osher, and Fatima. And in fact, these authors are all still very active. Stan Osher is a very well-known mathematician at UCLA in Los Angeles. What they proposed in '92 is this model. It's a very simple model in some sense, but it captures a lot of the essences, a lot of the essence of variational techniques. It's a cost function, as you can see here. A cost function that assigns to any function u, so u is also a function just like f, u is a function, and u is in fact an approximation of f in this model. An approximation which is computed by minimizing this cost. So for any possible function u, you can define a cost, you can just plug it in this expression and calculate its cost. How would you do that? Here you have an integral of u minus f. In fact, at every pixel, the pixels are denoted by x. At every pixel in the domain omega, I compute the difference between u and f at that pixel, square it, and sum over all pixels. That's essentially what's being done. So this is often called the L2 norm, or the quadratic distance. So this model basically says I fit a function u to f in a least squares manner because I'm minimizing the sum of squares. That's a quadratic data term. It's called data term because f is our data. This is the input observation data. And then in addition you have a second term, and this is characteristic of pretty much all variational techniques. They have a data term, and they have another term which is called the regularity term or regularization term. Regularization. That is the second term there. And that term basically tells us what functions u do we prefer among all conceivable functions without looking at the data. We want a function that is denoised. It should be similar to the input, but it should not contain as much noise. The key challenge, and this is an open problem in some sense, and a problem of endless research, is how do we know what the noise is and what the signal is? We have an image that is a superposition of signal and noise, but a priori no one tells you what the signal is and what the noise is. And so in practice, the way out is to make some assumptions about what is typical about noise and what is typical about the signal. And this is captured in the regularizer. What is typical about the signal, and this is the assumption that enters here, is that the signal is spatially smooth, which means from one pixel to the next, the color of the signal should be more or less the same. It shouldn't change too much once I'm moving. How do I impose that? I impose that by saying the derivative of u, so the change of the function u from one pixel to its neighbor, should be small. The next question would be, how do you quantify smallness? Right? I say it should be small. Here, they just take the norm. You could also take the squared norm. You could take lots of other measures of what means small derivatives. This, by the way, is the nabla operator. It's the derivative in the two spatial directions, but we'll learn more about that in the class. And there is a parameter lambda. This is called the weighting parameter. That parameter essentially tells you how much that smoothness constraint is imposed. And so typically in variational methods you have a data term, a regularity term, and a relative weighting between the two. What's important is we're minimizing this expression, and so sometimes you will find the weighting parameter here, but sometimes you'll find it in front of the data term instead. That really doesn't matter where you put it. In fact, if you divide the whole cost function by lambda, lambda is just a constant, then you would get 1 over lambda u minus f squared dx plus norm of lambda. So then you have the lambda here, and constant factors don't change the optimization problem. So if you have a constant factor, if you rescale the energy with 1 over lambda, the structure is exactly the same. And so the optima are the same, etc. So it's exactly this optimization problem and this one are the same problem. So if you read papers and you stumble over the fact that lambda is not here, but 1 over lambda is there, or some parameter mu is here and no parameter there, it doesn't matter. It's the same problem. This is important when we talk about optimization. Multiplicative factors in front of the energy don't have any effect on the problem. It's the same problem. Also, the addition of constant terms to the energy doesn't change. So if I take the same energy and add 5 here, doesn't matter. Because what I'm computing is the argument that minimizes this cost. And whatever minimizes this cost will also minimize the cost shifted by some constant. Right? Because these constants just have the effect that whatever your cost is shifted down a little bit. But the minima are still the same. Or the maximum. So this is a variational method proposed by Rudin, Osher, Fatemi, and what it gives you is this image. So it's an image that looks very much like the input, but it has no noise, or less noise. If you really go in, you still see a certain level of noise, but it's cleaner. This is actually quite nice. It's not terribly impressive to humans. Why? Because humans are very good at denoising. Our brain denoises things. So we are capable of actually removing that noise in our head. And that way you can easily see that this is a good solution because your brain can do the same thing. But nevertheless, for a computer, it's actually quite good because once we process and analyze input images, it's often better to analyze the denoise. If you do face recognition, etc., you may want to first denoise the input images to have a noise-independent recognition process. And that is a technique that you can use. As you can see here, this technique is more than 20 years old, which is ancient, really. But surprisingly, the approach is still extremely powerful. And it's not so easy to beat the Rudin or Fatemi denoising. There are nowadays more powerful algorithms that do better denoising, but it's not, these are very sophisticated models. One of the nice aspects of this Rudin or Fatemi model, and one of the reasons why it works very well, is that it is convex. Why this energy is convex, we'll see a little bit during the class. We'll talk about convexity, but to give you a first glimpse, the data term is a quadratic data term, and quadratic terms look like that. So that's a convex energy. The second term is not quadratic, but the norm of the gradient, norms look like that. It's also a convex. So that's essentially the reason why it's convex. Often when I give talks and they say the nice thing is this is convex, then later people come up and say, how do you know it's convex? So there is a little more involved in proving that this is really convex, but the essence is that these two, the quadratic and the absolute value are both convex. And then, as you can see, what we do is we are integrating these quadratic terms over all of omega. And integration is nothing but the summation. And convexity is preserved under summation. So if you have two convex energies, the sum of them is also convex. This is another nice property of convex approaches. You can concatenate some different convex approaches and you preserve convexity. So this is convex and this is convex, and the weighted sum is therefore also convex, assuming that lambda is not negative. With a negative lambda, you flip the whole thing and then you lose convexity. But negative lambdas would not be very meaningful here, right? What would that mean? If I would take lambda and invert it and make minus lambda out of it, so have some negative weight here, it would mean that I basically disfavor smoothness energetically. So I want an image that is similar to F, but is not smooth. And that's usually a very ill-posed problem. To come back to history, variational methods have, as I showed you, go back to the 17th century to the brachistochrone solution of Bernoulli. But that was one specific solution, very constructive as you saw, for one specific problem. And it's not easily generalized to arbitrary problems. So that actually came much later in the 18th century, and there are again many mathematicians and researchers that worked on this problem, but two of the most famous researchers or most influential ones are Euler and Lagrange. As you know, two of the most important mathematicians in history. And they devised very general strategies, very general solutions to variational problems. And so you can actually tackle the ROF model that we just saw with the techniques that Euler and Lagrange provided. The idea is you have this cost function, and what's important is to abstract a little bit from the concrete form of the cost function and to see, well, what do I have here in structure? It's an integral over the image plane, and then some cost that is aggregated for each pixel. What is that cost? Well, it is the quadratic difference of the color at that pixel to the color of f of the input at the same pixel, and it is the gradient of the function u at that pixel. So the gradient, I'll just write it as u prime, is the derivative of u. And so there are some, this is often called the Lagrange density, L. There is some expression that depends on u and u prime at any given pixel x. And the good thing is this canonical form of cost functions applies to that particular one, but to many others. So if I were to put nabla u norm squared, this is still of the same class of cost functions. And so what Euler and Lagrange devised is a framework to an optimality criterion for this class of cost functions. And it is something that you're all familiar with in high school, from high school, at least to some extent. As you may remember from high school, if you have, actually I have an image here. If you have an energy, E as a function of u, and you have here, abstractly speaking, your space of solutions, here's the cost for a conceivable solution, then the minimum is attained where the derivative of E with respect to u is 0. So that you know from high school, very simple idea, the tangent must be horizontal, the derivative which encodes the tangent must be 0. But another thing you may remember from high school is this is a necessary condition, it's not a sufficient condition. Why? Because the derivative is also 0 at local minimum. So not just for the global minimum, but also for the local minimum, the derivative is 0. And even worse, the derivative is also 0 at the maximum, which is really not what I want to have, right? If I'm solving the application problem by saying find the configuration of lowest cost, and then the algorithm gives me the configuration of highest cost, then whoever hired you to solve the problem will not be happy with that solution, because it's in some sense the worst solution. So you have to be careful not to compute maximum. And in fact, if you just solve the Euler-Lagrange equation, you might end up with the maximum instead of the minimum. So this is a bit tricky. It's a necessary but not a sufficient condition. And even more, what you can also have in addition to minima and maxima, you remember from high school, are so-called saddle point problems. Right? Saddle point solutions where you have something like that, where the tangent is 0, 0 is horizontal, 0 derivative, but you're neither at the minimum nor a maximum. So there's all sorts of nasty cases like this that can arise, but this becomes a sufficient condition once we know the energy is convex. Because if it's convex, there is only one minimum, and there are no maxima. And there are no saddle points. So with convexity, this is a sufficient condition for optimality. And this is why, in conjunction with convexity, the variational techniques really make a lot of sense. If you don't have convexity, I was saying one classical strategy is to compute the best local optimum. And this can be done by what's called a gradient descent. If these expressions don't make sense to you at this point, doesn't matter. We'll get into it in more detail throughout the class. So we'll actually learn how to compute Euler-Lagrange equations. This equation is called the Euler-Lagrange equation. Why is that? Well, maybe to put that beforehand, the difficulty here is the picture is very misleading. I'm really fooling you with that picture. Why? Because the space of conceivable solutions is not a one-dimensional space. This space that I drew here with the one axis is actually an infinite dimensional space. There are infinitely many dimensions to the function u. I can change u for every pixel. I can have a new value of u, and so these are all infinite dimensions, independent dimensions to my problem, and so that axis denotes an infinite dimensional space. And as you know, when doing derivatives in higher dimensions, you measure how much does your energy change in a certain direction. And so the question would be, what does it actually mean to say what is the change of energy with respect to u, if u is not a parameter but a function? And so this is often called a functional derivative, where I take the derivative of some cost with respect to a function u. And how that is done, what the techniques are, how to formalize this mathematically, this idea, this is one of the things we will learn in class. And we will also learn about what's called the gradient descent, but maybe to put that beforehand just so that you've heard the terms. Once you compute the functional derivative and set it to 0, what you end up with is an equation that is called a differential equation. And in general, a partial differential equation. And as a consequence, once I work on variational methods, any researcher who says he does variational methods will invariably also deal with differential equations and partial differential equations. In English, it's abbreviated often as PDE. So that stands for PDE stands for partial differential equation. And so we learn a little bit also about partial differential equations and a little bit about how to numerically implement partial differential. I should say all of these topics really are very broad. So for example, on numerical implementations of differential equations, if you want, you can take 5 or 6 classes on that topic alone. On optimization, for example, anyone who really wants to delve deeper into this matter this semester, there is a class in the math department by Michael Ulrich on particular kinds of differential equations and algorithms for minimizing these convex energies, also called primal dual algorithms. And a little bit also about the mathematics behind convex functions, etc. So there's a lot of related work that connects to us in the field of optimization, in the field of differential equations, etc. The gradient descent, we'll learn about that. The idea, I mentioned it, is that if you have, this is level lines of constant energy, so you can imagine some valley that is a little bit indicated here by these level lines of constant energy, and then you go downhill. This is the idea of the steepest or gradient descent. So you have an iteration of solutions, U0, U1, U2, and they go downhill. Again, the picture is slightly misleading. Here, the image indicates that the solution space has 2 degrees of freedom, so it's a 2-dimensional plane. In practice, again, as I said, we have infinite dimensions. But the concept still applies that you find a direction in that space where the energy goes down the fastest, and you just move step by step in that direction until it doesn't go down anymore. If it doesn't go down anymore from where you stand, then by construction you're at a minimum. Or maybe a saddle point, strictly speaking. But in practice, you know, numerically you typically are at the minimum. And so the gradient descent is a very general technique, and this is the equation of the gradient descent. For some reason I find it's a bit difficult for students sometimes to grasp what it means. It basically means the change of u in time. So I add a time dimension to the problem, an artificial time. It has nothing to do with the physical time. It's just a time that indicates that stepping process. And basically it says change u in time in direction of the negative energy gradient. The gradient, the energy gradient, the derivative is a vector showing in direction of the steepest ascent. The negative gradient is the direction of steepest descent. And so that says change u in time by going a step in that direction. It goes down. And this again is a partial differential equation, because now in addition to having derivatives with respect to x, the space parameter, we have derivatives with respect to time. And so you can compute this so-called Euler-Lagrange expression for the energy gradient, plug it in here, and then you can solve that equation, and it will lead you to a local minimum. If you don't have convexity, what you need to have is some good initial guess of your solution. Because if you start with an initial guess, then the local optimum is hopefully the right solution. For denoising, for example, a good initial guess is to start with the input image. Why? Because what I want is at least in terms of the data term, is something that is close to the input image. And so starting with that input is usually a good idea. So these are some of the key elements in variational techniques, and we will, as I said, learn more about how to derive these expressions, how to implement these during the class. Here's some applications. So as I said today, I don't want to get too technical. I'll just show you some glimpses of what you can do with variational techniques. And these are just a few representative things, maybe with a certain bias towards image-based reconstruction. We also work on many other problems in our lab, but these are some of the problems we work on. So I mentioned the multiple view reconstruction problem. The way it works, as I said, you have a set of images, typically not 7 or 8, but 20 or 30 images taken from a digital camera. And as I said, the problem is to convexify these things. Actually, it turns out you can do that. For example, in 2009, we showed that for 3D reconstruction, you can actually compute globally optimal configurations using convex optimization. How that is done, we may get into this a little bit during the class. Towards the end of the class, here is some applications. What it really means is that I can initialize arbitrarily. I don't have to know anything about the geometry in front of the camera. The algorithm will find the best conceivable geometry for that cost function that we see. And so these best geometries for our cost function for these sets of images look for, in this case, like that. So we have photographs, and as you can see, we can get fairly accurate, fairly detailed models of the geometry just from a set of images. Typically, as I said, this data set is not 3 images, but more like 20 images, or 25. Here is another example. This is, and actually an interesting maybe comment here. The good thing about modern image analysis, or one good thing in computer vision, is if you like this field and want to do research, there is very little overhead. All you need is a computer. You don't even need a camera today. For example, these images you can download from the internet. So you don't have to, cameras are cheap and you all have one on your cell phones and smartphones. But it's actually quite interesting that the internet is so full of images that you can do tons of fascinating image processing without ever buying a camera. There is nowadays algorithms where you can just type in a keyword, for example, Notre Dame, Paris, and the algorithm will generate a 3D model of Notre Dame. What it does, it Googles for images of Notre Dame, collects, and there are thousands and millions of images, collects them, selects a few appropriate images that are maybe color consistent in some way, and then does the reconstruction fully automatically. And so ideally, just by typing a single keyword, the machine generates a 3D model of that structure. Assuming, of course, that there are enough images. If you type in my house, it's not there. This is a project we did with a museum where we took about 20 images of these ancient statues, Greek statues. The challenge is this was a project in collaboration with an art historian. What they were interested in, there's about 20 of these statues all over the world, and they're more than human high, so this is about 2.5 meters high. They're very heavy. There's some in Bonn, some in Rome, some in Paris. The problem is you cannot get them all into one place. That would be much too tedious. And from an art historian's point of view, it is not known. It is known that they were part of an ensemble, but what is lost in history is the knowledge what that ensemble looked like, how they were positioned relative to one another. There is, now of course you would say, how would you ever find out? Well, actually there are certain allegorical stories about these pictures, they have meanings, and in addition in the reconstructions you will see it, they're very detailed in the front, but very little detail in the back, almost no detail in the back. And this indicates to the art historian that this was the viewpoint from which they were supposed to be looked at. And so you already know which direction they were most likely facing. And you can expect that they may have been looking at each other, the various statues. And so with our techniques, you can generate 3D models that you can interactively move around on your computer. And you can take another statue such as this one, generate another 3D model, and you can imagine once we have the 3D models, we can move them around in space, we can rearrange them and figure out what might be the most likely configuration. Something that you really wouldn't want to do with the real statues. Another thing, and this is, I think, an important aspect about image-based approaches and camera-based approaches, if you want to recover geometry of a structure, I believe the possibly most accurate technique nowadays is a laser scanner, because it gives you very detailed depth measurements and you can scan the object in great detail and resolution and get a good 3D model. So if all you want is a single 3D model of a fixed rigid object, take a laser scanner. But laser scanners have many drawbacks, and in fact nowadays in robotics, at least traditionally I should say, the laser scanner was the dominating sensor for robots. But that is changing very fast. Why? Because first of all, lasers are fairly expensive. And secondly, they're fairly heavy. For example, if your robot is a little flying quadrocopter or something like that, an airplane, then chances are you cannot put a laser scanner on top, or otherwise the thing will not fly off the ground. And then it's kind of pointless. So weight is an issue, size is an issue, and as you know, if you look at your own smartphones, cameras are cheap and cameras are tiny and lightweight. And they give very high resolution images. They also show the colors. A laser scanner doesn't tell you the color. So if you have a robot that is supposed to move around in the man-made world, you know, if there's a stop sign, the laser is not going to tell you what's on the sign. And so in some sense, the human world was made for the eyes and not for laser scanners. And so any robot that is supposed to move around in the world is better off with having eyes. But very important, one thing that is very hard to reproduce with laser scanners is to resolve 3D models over time. If you want to do action reconstruction. So here, for example, what we have here is two actors in a green screen room. They are filmed by about 16 cameras, and these cameras are synchronized. And this is a little bit of a technical effort to calibrate and synchronize so many cameras, but it can be done. And in fact, just recently, someone synchronized 40 cameras. So there's a high density of cameras showing you great detail of the scene. And where is this heading? Well, one of the things it's heading to is what's nowadays called 3D television. And so you can expect in the coming years, television will go into the third dimension. And you will be able to acquire actions in 3D in a way that the user can change his viewpoint later on. So you can watch your favorite action movie and you can say, oh, let me look at this scene from a different viewpoint. Why? Because you have a 3D scene and you can change the viewpoint interactively. And here's, and this is something that you cannot do with laser scanners. So these are not so professional actors, I should say. So I apologize, they're not very professional athletes, but what you can see is you can recover the geometry in fairly good detail at any given time of the video. And you can reconstruct an action at a rate of, I don't know, 25 frames a second. And this is just the geometry. I have a, I don't know if I have it in here. There is a video where I superimposed, this is Martin's work. He's actually, this is very recent. He did it 2-3 weeks ago, where he superimposed the color from the images, and then it looks even more nice. But as I said, you can reconstruct geometry at very good detail from cameras. What you have here is the rope of the rope jumping girl. If you look in the individual images, the rope is not very visible. It's actually very hard to see in the individual images, but still the algorithm recovers even fine-scale structures like that. And that's important because if you had in the reconstruction the girl jumping without the rope, everyone would say, what the hell is she doing? This is an important semantic detail. So, but you can see we get it at least more or less. If you look at the video, you see that the rope is broken up in places, but it's not fully connected. There are nowadays algorithms where you can impose the reconstruction should be connected, because pieces of rope are not likely to fly around in the air. They have to be connected somehow. You can impose that, but then your algorithm will be limited to that connected structures. And then if something is flying around, it will connect it. So these are interesting algorithmic challenges, and you can tackle all of these problems with variational technique. Here is another example, somehow the extreme case, if you are not willing to synchronize tons of cameras, and if you're not willing to get so much image data, one extreme case you can look at is a problem called single view reconstruction. And that is the case where you just have one image, a single image, and the question is, can you generate a 3D model of that area from just one image? Of course you would say, not really, because I don't see the object from multiple viewpoints, but as a human we can do it. As a human we have some guess at what that object looks like. And so an interesting question would be, how can we do that with a machine? In a maybe somewhat interactive manner. There are actually techniques that generate 3D information from images. I will not go into detail here. One of them is an approach called shape from shading, something you're also familiar with. If you look at, say, a white pillar, and it's illuminated from a certain viewpoint, then the coloring, the brightness changes, right? If it in locations where it faces the light is very bright, and wherever it doesn't face the light, it's darker. And from this illumination changes, you can generate 3D, even just having one image. Unfortunately, these techniques today are not applicable to real-world images, outdoor images, because you don't know what brightness changes are due to lighting effects, and what brightness changes are due to the fact that the colors are. Of course, you see a shadow here, right? And that would indicate something about that there must be a wing that casts this shadow. But what if someone had painted the grass darker? Possible, right? So of course there's ambiguities, and this is very typical for any kind of computer vision, that there's always infinitely many possible explanations for the images. But the challenge is to find the most likely explanation. And that can be done with the regularization. Ideally, among the many solutions that explain the image data, you want the one that is most likely. And this aspect of most likely is really what is encoded in this regularity. Here, what we propose is a very simple solution, but a variational solution. The idea is you find a surface S in 3D space that has minimal area. For any conceivable surface, I can measure its area, and this is what I denote by norm of S. And so I say, find among all surfaces the one with minimal area. That is it. Since surfaces form an infinite dimensional space, that is a classical variational optimization. In fact, a very old one also. In addition, of course, if I say minimal surface, then I will get a really flat object because that has the lowest surface. I have to impose some additional constraints. This constraint, pi of S is S0. Basically what it's supposed to say is that the projection of that surface should match onto the image, should match the silhouette. So I'm assuming that we can extract the object silhouette. And so the analogy that we have here is that of a balloon, where you extract the silhouette, you place a balloon inside the silhouette, and then you blow blow air into the balloon. And then you get some kind of roundish 3D model, but it is a 3D model. And the air that you blow into it, the amount of air, let's call it V0, and so the volume contained in the surface should be exactly whatever air. And that is the one user-specified parameter. How much air do I blow into it? If you blow more air into it, it will get thicker. And so with this one line, I have encoded the single view reconstruction problem as a variational problem. And so in variational techniques for computer vision, there are two aspects in any research topic. The first aspect is to construct an appropriate cost function or optimization problem, maybe this one. So there is a cost function and there may be constraints to the optimization problem. So it should be minimal surface, but in addition it should contain a certain volume and it should be silhouette consistent. The second aspect of variational optimization techniques is then to solve that problem. To find, once you formalize it in this mathematical way, now find the surface that fulfills these constraints, that minimizes this energy under this constraint. And that is often a numerical optimization problem, and this is then where the Euler-Lagrange calculus comes in, and the discretization of differential equations that actually leads to the numerical solution. Here is examples of the numerical solutions we computed with that approach. A balloon model works well, of course, if you have a balloon. Hopefully it will also work for non-balloonish structures, and as you will see, it does to some extent. So we assume that we have the silhouette, we place a balloon, we blow some air into it, and these are the 3D models we get. This is just the 3D model we computed, but in addition we can of course take the colors from the image and project them back on the 3D model. And this is what we show here, and so what you have here is an almost 90-degree view of the same object. So that's the most extreme, in some sense, viewpoint change that you can do. And you see, it's at least fairly plausible. So just from one image we get a 3D model. And in fact, what we showed is with recent hardware, you can actually implement this on a single PC in real time. So in a fraction of a second, you get your 3D model. Here's another example to show you a little bit what the volume term does. That is the one parameter that the user has to specify. These are reconstructions of that arch, with the texture, I should say, computed from for different volumes. So this is for one volume, this is for increasing volume, and yet increasing volume. And what happens is the thing just becomes thicker. At some point you would say this is not plausible, but somewhere in between it may have the right volume that you would like, and then you have a plausible 3D model. This is not going to be a metrically accurate 3D model, meaning if you really go to Arches National Park and scan the arch in, you will find the geometry looks different from what our model suggested. But it's at least a plausible guess at what a 3D structure is. And as I said, it's very easy and fast to compute. Here is other examples. This is a teapot case, so we have this one image from the teapot, and we can generate a 3D model and look at it from new viewpoints. And the model, as you can see, is actually fairly plausible. And once you have a 3D model, I mentioned that in the beginning, you can do things. You can change the illumination, you can change the material properties, you can take that teapot and relight it with different material properties, such that it looks more shiny, that it looks like it's varnished, or that it looks like, you know, different materials. This is, I think, aluminum. So there's a lot of people have devised already reflection properties of different materials, and this for us was actually quite straightforward to apply these different illumination techniques to the object. And so you can generate completely new models, views, and appearances of an object that you've only seen in one single image. This project, I should say, was done funded and done in collaboration with Microsoft. Microsoft, actually, the co-author on this paper, Karsten Rother, what he did is if you have the latest version of Office, at least 2010 or more recent, there is a technique in that allows you to copy-paste objects from photographs. You can extract, say, a person from a photograph and copy-paste it to a new photograph. And this is actually Karsten's algorithm that they incorporated into Office. With the algorithm we did here, you can not only copy-paste objects from one image to the other, but you can turn them in 3D, you can relight them, you can change the material. It's not yet in Office, but I don't know, maybe Microsoft will implement this at some point.
Is this reasonably robust, or is it?
It is reasonably robust, but there are several assumptions. One key assumption is that we have side views of the object. So we assume that the object is symmetric to the image plane. We do that because we only see the front, we don't see the back. And so to get a full 3D model, we have to make some assumption about what it looks like on the other side. And so we assume that it's symmetric to the image. The second assumption is that the objects are fairly round. So if you take something like a car or something that has very sharp corners, these are likely to get rounded off in 3D. With the balloon model, you get very blobby structures. So the next step would be to generalize that to more sophisticated surface. But otherwise, it works fairly robustly. Here's an example with the airplane, and here you see reconstructions that were generated just from that one. Now these don't look blobby, at least the wings don't. What we added here is you can see the user marked these scribbles. These scribbles tell the algorithm to modulate the minimal surface property locally. In other words, to stay in the analogy of the balloon, what you do is you assume a balloon-type surface, but the surface thickness is made thinner in certain locations so that you can allow protrusions. You can imagine if you have a balloon that has an inhomogeneous material, it will expand more in some areas and less in others. And so by marking here, we say decrease the surface cost in that area, and that will create these protrusions. So, but I should be honest, at this point it becomes a little more interaction for the user. It's not just giving the amount of air to blow into it, but it's also modifying the protrusion cost in different locations. And so Ino Töpper, who did this in his PhD, he and Martin as well, they have quite some experience about how to interact to generate certain desirable surfaces. But if you start, it's a little bit tricky to find the right parameterization to get the certain effect. But there are some, 3D objects like the bug here or the bird, where you don't need any such additional constraints, and where just the volume and the silhouette are sufficient to give you 3D models like this one. And so quite naturally, the surface, minimal surface constraint has the effect of if you have bigger areas, it will inflate more than with thinner areas. Next thing that you can do with variational techniques is you can not just estimate geometry, but you can estimate the color on the objects. So here, for example, I showed you we can take images and then we can reconstruct the object by minimizing the energy, and this is actually a gradient descent. What you see here is a gradient descent. Maybe I'll run it again. We initialize randomly in a block, And then the gradient descent in the space of surfaces, you move the surface in such a way to better fit to the image field. And once it's converged, means any modification of the surface doesn't lead to an improvement of the matching person.
I hope this is not a stupid question, but is the camera geometry known? So does one camera know where the other stands?
This is actually a very good question. The question is if the camera locations are known and how they are facing the scene. Yes. So for these reconstructions, we assume that we have the cameras. So the idea being that you fix the cameras and you can calibrate the location of the cameras beforehand. In a lot of computer vision challenges, image-based reconstruction problems, you don't have the camera location. For example, the museum's reconstructions of these statues, we really walked around the scene with a handheld camera. And then all we had is the images, we don't know where the camera was. And it turns out that the reconstruction of geometry and the estimation of camera locations is a nasty chicken and egg problem. Meaning if I know one, I can estimate the other and vice versa, but computing both at the same time is very difficult. There are algorithms that do it. It can be done. It works in practice, but it's never been put in a convex form. Meaning the algorithms that are around, they work fairly well, but they are not provably optimal. And I have to date not seen a solution to this problem. So what we did for the statues in the museum is we first ran one algorithm to estimate the camera locations, and then we ran a second algorithm to reconstruct the dense geometry. But as you saw with the statues, it works, but in some sense it would be best to do both at the same time. I have not to date seen the optimal solution to this problem. But as you saw, we can reconstruct geometry at a fairly good level of detail. Here's the rabbit, the reconstruction. Fairly good means you don't have the structure in the eyes, you don't have the details in the fur, but it's okay. One of the things you can do to at least improve the visual appearance of the model, the question is always, what do you need the 3D models for? If all you need is to create new images from a different viewpoint with changed surface material properties or changed illumination, so you don't actually need the true geometry but just the appearance from a new viewpoint, then you can cheat by computing not just the estimate of geometry but an estimate of the color on the surface.